Um, looks like he has video off, or it, like goes on and off.
Really?
Oh, there he is. No, he left.
All right.
Okay, you ready?
Mm-hmm.
So I'll start off with number one.
Okay. Sounds good.
A true breeding pea plant with round and green seeds was crossed to a true breeding plant with wrinkled and yellow seeds. Round and yellow seeds are the dominant traits. The F1 plants were allowed to self-fertilize. What are the following probabilities for the F2 generation, assuming independent assortment for the two traits?
Mm-hmm.
So I originally got A wrong because I mixed up what was dominant and what wasn't. But
Okay.
it's supposed to be 3 out of 16.
Yeah.
So
I'm trying to. Let me pull up my other one too, so I have the other my answers. But okay. So 3 out of 16.
yeah, because you could have those two different genotypes that would give you the yellow
Mm-hmm.
with one of the, and there's only one genotype that you get the yellow. So it should be like 1/4 times 1/4 would be 1/16 plus 2/16 for the other one to give 3/16.
Yep. Makes sense.
Okay. And then 3 out of 3 F2 plants with round yellow seeds. So to get the probability or to get round and yellow would be a 9/16. So you times that 3 times. So that would be 17.8%.
Yep. Yep.
Then C, an F2 plant will have either round or yellow seeds or wrinkled green seeds.
And that you do just 9/16 plus 1/16.
Yep.
Because you have 1/16 chance of getting wrinkled or green seeds because they're both.
Yeah.
Yeah.
And I guess you could say that one uses a sum rule because it has or in it. So you add the probabilities of each type.
Yep.
Then an F2 plant will not have round yellow seeds. So you just take all the ones that can't. And so I just did 16 out of 16 minus 9 out of 16 because I knew 9, you have a 9 out of 16 chance of having the round yellow, and got 7 out of 16. So
cool. Then so on the next one, on my answers, I guess I didn't write them out the same way. I actually, so you know how it says like she did this like 9/16 to the 4th.
yeah.
I did those. I just actually multiplied it out. So
Yeah.
okay.
That's what I did too.
Yeah.
So do you want to take the lead in number 2?
Yeah. So that one, you get 9/16 to the 4th, and that equals 0.1 or 10%. Do you always have to answer it in percentage? Does she want that?
I have never figured that out. So I usually just do both.
Okay.
Like I usually do like my like fraction answer, and then both, and then the percentage.
Fractions.
So
yeah. Okay. Then the next, so for that one, it's because the probability of getting all dominants 9/16. Then you times that by 4, and it gives you that. And then the next one is what's the probability of the first 4 are either tall or white. And you do 3/16, and then 1/16 because that's the probability of having it being all recessive.
right.
Oh, and 3/16 because that's what it is for heterozygous.
Mm-hmm.
and then multiply by those by 4, you get 0.1%. And then what's the probability of that if 7 F2 plants are produced, 3 are tall white flowers and 4 are dwarf white flowers? So this one, her answers on it, I thought, oh no, I think I must have read that one wrong.
Yeah, I did see wrong too, but it looks like it's I don't remember what that's called, but that equation.
It's the binomial.
Yeah. So I think it's like an example in the notes. It's like how many, like if you have 2 out of 5 kids have blue eyes, what's the probability of that? So I think it's just like recognizing that it's that type of question.
I did it that the first, in my head, that it was asking that the first 3 were tall, so I didn't do the binomial.
Right, kind of like B. That's how I did it.
Yeah. So I just I read that wrong.
Yeah.
One. And then the next one was, what's the probability that the order of the phenotypes observed? Plant 1 is tall and purple. Plant 2 is dwarf and white. Plant 3 is tall and white. Plant 4 is tall and purple. And plant 5 is dwarf and purple. So you got 2 of them that are homozygous dominant. So those ones are 9/16. Then you have 1 that's homozygous recessive, and that's 1/16, and then 2 that are heterozygous, so those are 3/16. And so when you add them, multiply them all together, you get 6.95 times 10 to the negative 4th, or 0.0695%.
Yep.
Yeah. Okay. And then I didn't quite understand how to do this one with the chi-squares.
Number 3.
And the null hypothesis, yeah.
So like to form a null hypothesis, you pretty much just state like what's in there. So like you say what's dominant and what's recessive, and usually you can tell that by the listed offspring.
Okay.
And sometimes it will even tell you in the statement and stuff.
Yeah.
And then like if it follows Mendel's laws and like the ratio it would follow.
Okay.
That's how I did it.
Okay. So that makes kind of sense, and I kind of did it the same way.
Yeah.
So how do you take these ones then and put them into the chi-squared? So what is the I guess so right there you have given in the question, you have the observed values. So how do you know which ones are the accepted values?
So the expected values,
Yeah.
so you have the ratios of what it should be, and this one would have been 9 to 3 to 3 to 1, and you times each one of that by the total amount of offspring produced. So if it was like 100 offspring, you would say 9 divided by 16 times 100. And that would be the expected offspring that should have that trait.
Okay. So I just didn't understand. I just didn't know the expected one was.
Yeah.
So,
I mean, does that make sense now?
Yeah. And seeing it now, I realize it should be 9331. So.
Yeah. Okay.
And then put those all in, you get 0.543, and that's over 0.05 or 0.5, so you fail to reject the null.
Yeah, so it's when you look at the values, you go to the degree, say it's like degree 2, and it's the stuff that's in the chart, right, that you look at for the numbers.
Right.
Like not what's ever above. I don't know what those numbers above are. That goes to like 1 or something.
So if it's over, yeah, actually I don't I don't understand that
So I think
either.
it's the stuff that's in the green and not, you don't pay attention to the top of the chart. That's what I was confused on. But,
Okay.
probably
Okay.
just made it really confusing now.
All I know is it's got to be if it's greater than 0.5, right? Then you
Mm-hmm.
reject it, and if it's less than 0.5, you fail to reject it.
It would change according to the chart. Let me find the chart.
Okay. They didn't teach you that chart in biostats.
Okay. So I pulled up the chart from the PowerPoint.
Okay. So is
And
that
so you had the degrees of freedom on the side. So if you have this has 4 different traits, it'd be 4 minus 1. So it's the degree of freedom 3.
okay?
And then if you go over and it's in the light area, your number. So we had 0.5 something. And you're like, okay, that fits somewhere in here. If it's between the 0.352 and the 1. And you're like, okay, it's, we fail to reject it. But if it's higher than for 3, it would be 4.6.
Mm-hmm.
So we would reject it. And it changes per degree of freedom.
Gotcha.
So at least that's how I figured it out.
That makes sense.
So
Okay. So we failed to reject that one.
yeah.
And then on 4, that one is autosomal dominant. And that's because there's one parent in all of them that contain it. And then it's autosomal because not all of the offspring, I think the female offspring in that one, contain it. So it's autosomal. If all of them contain it, then it would be X-linked dominant.
Yeah. So how do you figure these out? Because I usually just kind of write down what I see.
Yeah.
I see males and females can get it, so that we'll cut off Y-linked. Then every generation usually means it's dominant.
Yeah, that's kind of what I did.
That's okay.
What I did too. I just watched that video that had the flow chart.
Mm-hmm.
And so yeah, and I just kind of went through it. So this one, it's dominant, right? Because every single parent has one.
Mm-hmm.
And then if it said something like if every single female out of the offspring of an infected male contained it, it would be X-linked. But in case this one doesn't have all the females, there's one that doesn't, then it's autosomal.
Okay.
So autosomal dominant. Then this next one was X-linked dominant because all the females of an infected male carried it.
All right.
And it's in every generation, so it's dominant.
Mm-hmm.
Then the next one's X-linked recessive, and that's because it skips generations. So if it skips generations, recessive, and then it's only with males, so it's X-linked. And then the last one is autosomal recessive, and that's because it skips generations and both male and female had it.
Yeah. So.
All right, last one. And this is another square one, so I didn't quite understand.
I think I got this one all right.
Okay.
So, let's see. So you were first to use the chi-square test to determine the Q-naughts results.
Right.
And then see if you were rejected or not. And doing it, you go through the expected through, the observed minus the expected.
Right.
And you got how to do that now, right?
The 9-3-3-1, right?
For this one, because it's a 3-to-1 ratio, because you only have those two traits. You have just one dominant and one recessive.
Okay, so it's 3-to-1.
Yeah, so it depends on like how many traits you have showing up.
Oh, it says that, yeah. Okay.
And doing it would, you get for your chi value 1.257, which I believe you would fail to reject it. Yeah, you failed to reject it.
Yeah.
And then you went through Castells and Little's observed ones, and you would reject it because the chi value would be 60. I got 68. And that's the same on the other answer sheet, which is way too much. And so you would have failed. So you would eject the hypothesis.
Yeah.
And then you combine them both. So the observed from both of the tests. And you'd find again that you would reject the hypothesis, the null hypothesis.
Okay.
So number D is provide a hypothesis that best explains the inheritance pattern displayed by the yellow coat trait in mice. So I figured it was a 2-to-1 ratio instead, because I kind of just like took the there's 1,063 of the yellow mice, and divided that by the total mice.
Mm-hmm.
And I believe I was about around 70%, and then I did the same for the gray, and that was about 30%. So I figured it would be a 3-and-1 based on that. I mean, a 2-and-1.
Okay.
And that's what I had further on the teacher's answers. It said, when a mouse is homozygous for yellow allele, death occurs. So obviously one homozygous would be deathly. So.
Yeah. Well, cool. Sounds good.
Okay.
I understand that chi-squared a little more now.
That's good. Because I'm sure it'll be on the test.
Yeah. Okay. Well, good luck on the test.
You too.
All right.
Bye.